about the frustration and multi-orbital effect in multi-insulator and superconductors.
Thank you. So what I would like to do in these 3/4 of an hour is to give you an ab initio point of view of a few interesting properties in solid-state physics. In particular, I will concentrate on as examples the new iron-based superconductors, and also, if I have time, I will talk about a class of Mott insulators that show what is called geometrical frustration, and will tell you how, from DFT, from density functional theory calculations, you can learn information about the microscopic structure of the systems. And what I also want to show you is, in fact, which are the limitations of density functional theory, and what kind of improvements of density functional theory are being done nowadays in order to be able to describe this kind of systems. So we're starting with our main subject is solid-state physics, and as you know, we have to deal with interacting many-body systems. We have 10 to the 23 atoms, and in fact, we, at the very end, we deal mostly with the electrons in a cubic centimeter. And what is interesting about these solid-state systems is that we have the simultaneous action of several degrees of freedom, the spin of the electron, the charge, the lattice effects, and the orbitals, so that we can have more than one orbital that are playing a role in these systems. And this is what I will concentrate today also, and see how we deal with multi-orbital effects. And the interplay of these different degrees of freedom give rise to competing ordered phases. And I will show you some of examples of these competing ordered phases. Mostly interested we are in solid state in strongly correlated materials. So these are systems where the electrons strongly interact. So we can describe that in terms that the many-body electron wave function shows a very large entanglement. And there is a class of materials which are called the Mott systems, which, as I show in here, due to this strong electron correlation, they are insulators instead of being metals, what you would expect. So in principle, you know that in a metal, we have that the electrons, there is strong screening effects, and you can basically in a metal consider the electrons like moving almost independently. But if these electrons, the correlation of these electrons is strong, so if they really, the screening effect is not that high, what happens in systems that you would say this should be a metal because you have what is called a Hall field system, these systems are in fact insulators. And these are these kind of insulators that are insulated because of the strong correlation are the so-called Mott insulators. And starting with these Mott insulators, we have a very prominent example of Mott insulators, and these are the high temperature Fuchs superconductors. The systems, as you know, they were first discovered in 1987, and they are basically, if you look at the structure is based on copper-oxygen planes, and then we basically have between these planes either bismuth, strontium, calcium, depending on the structure we are considering. But the most important part of these systems are these planes of copper oxide, copper oxygen. And here what I'm just showing is the coppers, where copper is here in the so-called 3D9 configuration, so we have basically one hole per copper. And when the system is in what is called the parent compound, it's not DOE, these systems are just antiferromagnetic Mott insulators. So they are insulators because we have 3D electrons, we have strong correlation, and the system just is insulated. But now when you start doping the system, either by just here changing the amount of oxygen that you have, in the case of this viscous system, this translates into the fact that you add here some holes in your planes of copper, and therefore you start having transport in these planes, and the system at some critical doping gets superconducting. And as you can see, we have here a very large variety of different phases in this phase diagram, temperature versus docking, depending where we are. So from antiferromagnetic insulator to superconducting to strange metals, so non-fermi liquid-like, and in the overdot regime to the Fermi liquid-like metal. So this system, as you know, was given the Nobel Prize in 1987 to Bernath and Müller, but from the theoretical point of view, we still don't have the theory of superconductivity for these materials, and the reason for that is this strong Coulomb repulsion, which is very difficult to deal with, and this is why in the last 25 years there has been a large amount of improvement and of development in order to deal with this interaction. So if anybody is able at some point to really solve the problem, then surely there will be the second Nobel Prize for superconductivity in this case. So this is one prominent example of Mott insulator, that by doping the Mott insulator you get it superconductor. And let me just, since I'm going to talk later on about frustration, let me just tell you about one effect that is usually encountered in a few families of Mott insulators, and this is frustration. And here what I'm showing is magnetic frustration. So we have few systems like the spinel systems, where we have here that our ions here I'm just showing the spin 1/2, are basically in a triangular or in a tetrahedron configuration, and they would like to be antiferromagnetically ordered. So as you can see here, if these two like to be antiferromagnetic, and the third one has a problem in being antiferromagnetic with this one and with this one at the same time. So this is the situation of geometrical frustration that we encounter in a few Mott insulators. So the frustration is the inability to satisfy conflicting interactions, and as a consequence of that, there are a lot of, the system is very sensitive to weak perturbations, so the system is very unstable. As you know, you don't like to be in a frustrated state, also this you could translate it also in psychology. So the nature tends to get out of this frustration, and any small perturbation to the system will just make the system go away from this frustrating state. And interesting about frustration is that you have effects of criticality, you have coexistence of complex orders, and what I will be talking a little bit about is about orbital frustration. So you can also have frustration at the level of orbitals. So due to these discoveries that we had 25 years ago, there has been a lot of intensive activity, both from the experimental point of view and also from the theoretical point of view, in order to understand these strongly correlated systems. And there has been a lot of efforts in order to get new unconventional superconductors. And one of the most interesting discoveries in the last years have been these new iron-based superconductors. You already had, I've seen a few introductory lectures about them. I'm just going to remark here the properties that I would like later on to describe in terms of density functional theory. So what is interesting about these materials, so if you look at this, at the structure of the materials, and this is the so-called 1111 materials or 1111 systems, where you basically have these planes of iron surrounded by arsine, and these planes are separated by, in this case, planes of fluoride, lanthanum, and here oxygen. So what is interesting about these systems is that, contrary to the cuprates, in the cuprates, what was important, as I was telling you, was the copper and the oxygen. So these are the two basic elements that you have in these ITC materials. Here, what is important is these planes of iron and arsenic. So oxygen is not playing a crucial point in order to get this to understand the behavior of these systems. And now let's look at the phase diagram for these systems. What one sees is at, basically when the system is in the parent compound, so I don't do any doping to the system, I don't apply any pressure. The system is at high temperatures in a tetragonal phase, and it's metallic. Now going down in temperature, one has at about 154 degrees Kelvin a structural phase transition from this tetragonal to the orthorhombic phase. And now we're going down in temperature until 140 Kelvin, the system orders antiferromagnetically. But contrary to the cuprates, here the system is still in a metallic state. In the cuprates, we have that the parent compound is insulators. Orders antiferromagnetically, but it's insulated. Here, we have that the system remains metallic. And now if we start doping the system, in this case, what one observes is that the system goes into a phase transition from this antiferromagnetic spin density wave into a superconducting state. So it looks very similar, the phase diagram very similar to the case of the cuprate superconductors, but as I was telling you, there is here quite a few crucial differences, like the fact that this is a metallic phase. Here also, as you see, we have these two structural and magnetic phase transitions. There is a lot of discussion about what happens in this region, whether we have pneumatic phases or we don't, since, as I will show you in the next transparency, other families of these iron-based superconductors don't seem to show this region between the structural and the magnetic phase transition. So this is still under discussion what's going on here. But again, you have, these are so-called 1 to 2 compounds. Here are, in this case, we have again displays of iron arsenic. And instead of displays that we had in the previous compounds of lanthanum oxygen, here what we have is barium. And when the system is doped with potassium, then again we get a system superconductor. Another important point about these materials is that they can, one can get them superconducting either by doping the system or also by applying pressure on the system, as it is shown here in this generalized phase diagram. By applying pressure on the system, one also obtains transition from this antiferromagnetic spin density wave metal into a superconducting state. And again, we have also these magnetic phase transitions are also accompanied by structural phase transitions from tetragonal to orthorhombic. So now, of course, our question is, how can we understand the behavior of this variety of systems that I was showing to you in terms of a microscopic description? And in fact, as you saw, many of the systems I have shown to you, there are systems where electronic correlation is important, so we have to see how we deal with this effect. So if we start from really what is called ab initio first principles, it means that basically the only thing that we have to consider is that we have a crystal where the atoms sit in a certain symmetry ordered state, and then we have these atoms have a certain nature, and we have the electrons of these atoms, and we have to basically write down the basic interactions between the ion-ion, electron-electron, electron-ion. So of course, one starts with the many-body Schrödinger equation, and here I already did two approximations. First of all, I did Born-Oppenheimer, so we considered, as you know from solid-state courses, that we separate the ionic system from the electronic system, and we deal now only with the electronic Hamiltonian. And the second approximation that I did is, first of all, I'm going to consider non-relativistic electrons, so I didn't include here the spin orbit effects, otherwise we should start with a Dirac equation. So basically, our Hamiltonian, as you know, this is the stationary Schrödinger equation where we have the kinetic energy, the interaction between the electrons and the ions, the Coulomb interaction, attractive, and the electron repulsion. And due to this term here, this, to solve this many-body equation, needs to solve these 10 to the 23 coupled equations that we don't know how to do that. So that's why we have, in principle, two options to deal with these systems. One is to use the ab initio density functional theory, which is an effective one-electron approximation. And there is another possibility, and this is to consider effective models. So that means once we have our phenomena, we just try to, first of all, identify which are the minimal interactions that we should consider, and write that down into an effective model that we can then treat by using many-body methods in order to to have a better description of the Coulomb repulsion. And what has been, of course, being done in the last 10 years is the combination of the advantages of doing density functional theory and the advantages of doing effective models. And this is what I want to tell you a little bit. So, since I was told to tell you a little bit of basics, probably you know that, but let me just go through it in order that we see where do we, in fact, are good when we are doing density functional theory, and where we should be careful when using this approach. So density functional theory is based on the Hockenberg-Kohn theorem, which states that the ground state energy of a system of interacting particles is a function of the ground state density. So it means, and this is a theorem, that it is enough to know the ground state density of the system. I don't need to really know the whole many-body wave function. So with the density, I can really find out that there is a functional that describes the ground state properties. And in fact, one can generalize this theory into a more general concept, which is that any property of the many-body system can be viewed as a function of the density. So this is, as you see, as a very strong statement that we don't need to have this 10 to the 23 degrees of freedom. Is enough to have only the 3 degrees of freedom of the density in order to be able to describe all the properties of my system. But the problem is that we don't know how this functional looks like. So this is a very powerful theorem, but at this point it's useless because we don't know how to write that down. And a very important contribution of Kohn and Cham was, in fact, the local density approximation. In fact, Kohn got the Nobel Prize a few years ago because of the density functional theory as well as LBA. So the idea from this ansatz, from this local density approximation, or the idea from Kohn and Cham is basically this is functional that we know we exist, and this is the density of our interacting system. So we replace this interacting many-body problem with a non-interacting problem where all the many-body effects are in fact included in this exchange correlation functional. So since I know that this functional is a unique function of the density, so what we do is we map this complex interacting system into a non-interacting system where we can now write down the functional as a sum of functionals that we know, the kinetic energy. This is the external functional, which takes into account the interaction with for instance, with the lattice. This is the Hartree functional, which takes into account the electrostatic interactions, as is written here. And here, in this exchange correlation, we include all effects of exchange and correlation that, again, we don't know how to write that down. I mean, so we have translated this one functional into all what we don't know inside this functional here. Now, of course, since we are in this fictive non-interacting problem, we can write the density as a sum of one particle densities, so that with this sum we can decouple and get a set of equations, one for each particle, Kohn-Cham. I mean, these are the so-called Kohn-Cham orbitals, and therefore we have managed to decouple this many-body problem into one-body problem. That's why density functional theory is an effective one electron or one particle theory. Now, of course, as you see, this is a self-consistent equation because the Hartree term depends on the density. And here in the exchange correlation potential, we don't know how it looks like. So this is, in fact, it should be, this is variationally derived. So it should be, in fact, as the variation of this exchange correlation functional here with respect to the density. And here now is where Kohn and Chan proposed the local density approximation and so in order to approximate the exchange correlation functional. And nowadays there are a lot of different suggestions or proposals in order to get this exchange correlation functional. So one is the local density approximation, the generalized gradient approximation, and there are plenty of them. Quantum mechanists have done a lot of work on that, and also the solid state physicists. And of course, some of them are better for some kind of systems, and others are better for other kind of systems. But as you see, basically, these are the basics of density functional theory. But at the end of the day, where we do approximation is in the exchange and the correlation of the system. So that what do we, in fact, what are the advantages of density functional theory? So this is a first principles method. As you saw, the only input is the initial atom's position. This is the only thing we need to know, what kind of atoms are in our system, and then all the interactions are already included in these Schrödinger equations. And what kind of information do we get out of these density functional theory calculations? So we get information about the electronic structure of the system, the charge density, so as I'm here, for instance, showing in a polymer, the bond structure, the chemical bonding. So these are all density of states. These are all the properties that we are going to deal with when we do density functional theory calculations. But of course, as you saw, electron correlation is not correctly described. So if we want to describe systems where we know electron correlation is important, we have to be very careful when using density functional theory. So we have to know where are the limitations of this method. So now let me go to the other method that one deals with, especially when we are treating correlated electrons. What is the other way of dealing with them is to go directly to effective models. And there is one very famous effective model, which is the Hubbard model. In fact, the Hubbard model only contains two terms, as you see. So everything reduces. Here, I'm just showing these Q-crate superconductors and this basic structure that I was telling to you, this copper plane on a square lattice. We have basically one spin per lattice, and when we start doping the system, basically what happens is that we start putting holes into this lattice. So we have two important interactions here. So one is the kinetic term that allows the spins basically to hop, the electrons to hop from one side to the next, and the electron correlation is all put into this on-site Coulomb repulsion, so I need to pay an energy U if I want to have the spin going into state, and the state gets doubly occupied. So this is, as you see, a very simple model, but as you know, this model is only solvable in very special cases, and otherwise one has to treat this model by using various many-body methods. And in the case of exactly half-filled system, one can obtain from the Mott model the Heisenberg model, where we basically have the exchange interaction between spins. So one can use, there is a lot of different types of many-body methods that one can use in order to deal with these effective models, like motivation theory, multiorbital, big ansatz, renormalization group, numerical methods, many of them, surely you know them, quantum Monte Carlo, DMRG, transfer DMRG, and so on. And of course, one can get with the evaluation of these effective models, the thermodynamic, magnetic, and transport properties of your system. But these this effective model is, of course, parameter dependent, depends on your parameters, and depends a lot on your intuition. The intuition of just basically saying this is my system and these are the interactions I should consider. So there is, in this sense, sometimes one can be pretty off if one doesn't get a little bit more help of ab initio-like kind of approaches. So, and this is, in fact, the idea that has been developed in the last 10 years to include, so to basically take the advantages of both methods, the advantages of density functional theory, which deals, in fact, which has all the information of the bonding of the system, with this effective model treatment, which treats correlation, electron correlation, much better and properly as a density functional theory. So here I'm just showing to you in a scheme. The idea is basically from the density functional theory, by using either downfolding of the band structure or the tie binding methods, to derive then effective models that contain, because we derive them from density functional theory, so from basically this downfolding of the band structure, contain already the important interaction paths that you may have missed if you try to just do it intuitively. And then one can treat these models that contain already the information of density functional theory with many body methods in order to obtain a physical picture of the system. And one of the methods that is now being developed strongly is the combination of local density approximation with dynamical field theory, which considers then correlation and quantum fluctuations on a local level, and basically includes what is missing in the density functional theory calculation. So this is now what we are going to do, and I'm going to first concentrate on density functional theory for the two classes of systems that I showed to you, and we will see when we have to really go into such approaches in order to get a better description of the system. My time?
You have 13 minutes.
I have 30 minutes, okay. So let's see what, from the iron-based superconductors, what information do we get when we do density functional theory calculations? So one information that we get is, of course, we study the electronic structure of our system, and if we study the electronic structure of these iron-based systems, one thing that is clear, one feature that is clear, is that we have all the, so iron is a 3D, all the 3D orbitals are in fact playing a role at the Fermi surface. As you know, here the Fermi, near the Fermi surface are in fact is where all the low energy physics of the system is going to play an important role. So as you see here, I'm just showing here the band structure. This is for a 1 to 2 system along K path, high symmetry path in the Brillouin zone, and you have here the mixture of these different d orbitals at the Fermi level. So this is really a multi-orbital system. I didn't show it here, but if I were to show you, for instance, the band structure of these high T plates, one sees basically a nice copper dx square minus y squared band, and that's it. Basically hybridized with oxygen, but this is the only copper D band that plays a role at the Fermi level. This is not the case for these iron-based superconductors. So this is one information that we get out of these density functional theory calculations, and also the shape of these bands. And now we can extract out of that the Fermi surface. And what we see when here is, for instance, the Fermi surface is the gamma x and m point, is if you do a pi shift, if we shift now this pi, we have a perfect nesting of these here, these sheets at the gamma point with the sheets at the m point. And this is in fact, this perfect nesting is telling you that the system is unstable, has a pi instability, and we'll try to get rid of this instability. And one option is basically this spin density wave ordering that one observes in these materials when you go down in temperature. So one can understand from these density functional theory calculations this spin density wave ordering that the system show at low temperatures as a consequence of these nesting features from in the electronic structure. So what do we get right by doing density functional theory calculations in these ion-based compounds? So as I was showing to you, we get right the orbital occupancy and the relative energies in spectra. We get right the magnetic ordering. So DFT predicts correctly, which is the magnetic ordering of these systems at low temperature, but also DFT has a lot of properties. And here I'm just mentioning two of them. One is that DFT, when we are in this ordered phase, does a strong overestimation of the magnetic moment of the system. So here is these are the experiments of De La Cruz and collaborators, where one sees for this is for the 1111 system going down in temperature at about 150 Kelvin, the system orders, and here is where the magnetic moment starts to rise, and you see that this is very low. It doesn't really reach the saturation moment, so it's very small compared to what DFT will give you. And the second problem is that the electronic properties are extremely dependent on the position of the arsenic in these iron arsenic planes that I was telling to you. So maybe let me concentrate on that. Why is DFT having these problems in getting the correct reduced magnetic moment? And here I'm just using here basically itinerant arguments since we are in DFT. And what I'm showing here is we did a study of the magnetic moment as a function of pressure, which is the same as by just changing the volume of the system a little bit and just see how the magnetic moment of the iron changes, and also how it changes by changing the position of the arsine. And as you can see, the very small changes of volumes and position of arsine does do very strong changes on the value of the magnetic moment. So the magnetic moment in iron is very soft. If we do this kind of calculation for the cuprate system, the copper spin remains really very robust, remains this 1/2. Here, this is not the case. So here, what we see is that the iron, in fact, is in what we call magnetic instability. And how do we understand that? So in order to understand that, so let's look at the density of states. Here's the Fermi level, and as you see, the Fermi level, we have a large number of density of states at the Fermi level, and you know the Stirner criterion. So this means that the system is very unstable when you have a lot of density of states there, and therefore the system tends to get rid of this instability either by increasing the magnetic moment, so by increasing the exchange energy by spin polarization, or by just by increasing kinetic energy. So when we change the volume of the system, this is also a way of getting away of that, and therefore the system doesn't need to just highly spin polarize, and that's why the magnetic moment gets reduced very drastically. So we understand why DFT gives these very much changing magnetic moments. Nevertheless, this doesn't explain why these materials have this very small magnetic moment. And so there have been various suggestions to explain this reduced magnetic moment. Here, for instance, I'm showing the localized picture of Chimia-RC, where they propose, in fact, that we have in this system frustration, and it's true that we do have frustration. If you see here our iron d orbitals, and this is the arsenic p orbital, so we have that the J2 is an antiferromagnetic coupling, while the J1, so the nearest neighbors coupling between the irons, if you see here, this coupling is basically 90 degrees, so this is a ferromagnetic coupling, so we have here frustrating effect. And in fact, if you have frustration, also this reduces the magnetic moment, but this kind of localized model can never explain an antiferromagnetic metal, so which is what we have in the system. We don't have antiferromagnetic insulators, but we do have antiferromagnetic metals. And here is where the many-body the multi-orbital character of these materials come into play. And here I'm just showing an important fact about these systems, how the multi-orbitalicity plays a role, in fact, in defining the properties of the system. So if we look at the downfolding of the band structure that one has done, there are a lot of works where this downfolding was done, or tie banding models. Here I'm just mentioning some of them. One observes that there are weakly frustrated and highly frustrated orbitals. And when I mean weakly frustrated, let me just put it into this language of the Howard model. I mean that there are some orbitals where basically I have strong Niers-Neighbor interaction, where for some other orbitals I have strong next Niers-Neighbor interaction. So I have basically a TT prime model, and the idea now is to see whether the interplay between this multi-orbitalicity and the fact that I have also some frustrating kinetic terms, whether this is going to influence the magnetic moment of the system. And what we did is basically to consider the minimum model where we have a frustrated and a non-frustrated band with the corresponding Kunz coupling and the corresponding Coulomb repulsion. And we treat, in fact, this is very similar also to what Matthias Wojta also did together with Haeckel. And the idea here is now, let's try to understand what kind of phases do we get when we have these competing frustrating and unfrustrated bands into a material. And for that, of course, we have to deal with this with an anybody method. We did here dynamical mean field theory, and I just want to mention the following, that when we have this, basically here we have the unfrustrated band, so we will get, of course, an antiferromagnetic ordering. Now this is the frustrated band, where in fact hinders this ferromagnetic ordering, antiferromagnetic ordering, and due to the Kunz coupling, what happens then is that the system gets at some region of your phase diagram, at some small value of u, into a region where the system orders but still remains metallic, it's not insulating. So this could be an explanation that due to the quantum fluctuations and these frustrating effects between your orbitals, an explanation why the magnetic moment of these iron
Your magnetic structure is kind of checkerboard or
straight. No, this you have, oh sorry, my picture is basically, this is one orbital and this is the second orbital. So just look at it as orbital, unfrustrated orbital, unfrustrated orbital.
No, but I mean just in plane, you kind of when you record the video.
Strike, we consider strike.
But here it's kind of...
Yeah, this, it was well, it's because I, basically here, you mean the up, down, up, down. Yeah, but we consider strike corner, sorry about the picture. So now, so you see that in these iron-based superconductors, DFT helps us a lot, but this has its limitations. One limitation is this reduced magnetic moment, so here we have to go beyond DFT. Let me just show you another point where DFT is also showing to you that it's not enough. Here I'm just showing ARPES experiments from Richard and collaborators for the 1 to 2, so this iron arsenic to barium system that I was showing at the beginning. And here we have basically, you see the band structure around the gamma point. So we have this nice here band here and then this band here, and GGA is completely off. So if we do just density functional theory calculations in the generalized gradient approximation, one is completely off. Now one can cure that a little bit by doing GGA plus U. So here GGA plus U, you include the correlations at the mean field level. So one basically gets a better description of these bands, but here in this picture, we have already multiplied our bands by a factor in order to reduce them. Otherwise, these bands would also go pretty down. So we have to include, to renormalize the bands in order to agree with ARPES. Now let's go here into LDA plus dynamical mean field theory. What I was showing to you is combination of DFT with a many-body method. where here, in fact, there is no need of renormalizing your bands because here you include already these interactions, at least at the local level, and in fact you can get quite good agreement with Arbus experiments. So in these iron systems, correlations are important. They may not be as strong as in the pit rate, but they are important. Otherwise, one cannot describe a few features of these systems. So where is DFT? And I think my time is probably getting over 3 minutes. Where is DFT also useful for these materials? So where it's also useful is whenever you want to describe any kind of structural phase transition in the system. And as I told you, in these materials, superconductivity can also be obtained under pressure. And there were the first reports on superconductivity under pressure for these 1 to 2 systems that was observed in these different materials. And later on, there was a lot of discussion how good were the samples in order to get the superconductor. But what is important is, as you see, here's the phase diagram temperature function of pressure for this calcium 1 to 2, is that the system show, especially this one, this collapsed trigonal phase. So it's a different kind of structural phases. So these features can be well described by doing density functional theory calculations. And in fact, by performing structural relaxations at constant pressure, here I'm just showing for this calcium 1 to 2, where basically the idea is you just start with your structure and you simulate pressure and then calculate the electronic structure and the new parameters of your system. And basically what one observes is that these are the A, B, C, so this is A, B, and C is the perpendicular lattice parameters that at a certain critical pressure, we have here, this is the C parameter, which is what you will expect if you apply hydrostatic pressure. Here you have van der Waals kind of interaction, so this is the most compressible direction, and this is what we see here. While A and B is on the plane, this is less compressible, and this is what you see here. And at the critical pressure, you have this jump into basically a new phase, which is this, it's a collapsed trigonal phase, collapsed in the sense that the C-axis is, C over A is much smaller than what you would obtain by just in a trigonal phase. And let me just forget about these pictures because of time, but let me show you now the hydrostatic pressure in contrast to uniaxial pressure. And the reason why I'm showing that is because in experiments there seem to be a lot of difficulties into getting hydrostatic medium, and there is a lot of discussion whenever experiments come out whether it's, and these are, I guess, experimentalists in the audience will answer that much better than me, but there is a lot of discussion about how hydrostatic are the conditions, whether there are non-hydrostatic effects. And this, what I want to show you, is that the phase transition, the structural phase transition, can change drastically if you have some level of non-hydrostaticity in your system. So again, here for this material, one gets also this structural phase transition. This is a magnetic phase, and this is a non-magnetic phase from orthogonal to collapsed trigonal phase, but at a much lower pressure. So it seems that the uniaxial pressure is much more effective in order to get this phase transition than the hydrostatic pressure. You probably will ask here, what about superconductivity? Of course, I'm doing here the density functional theory calculations. We cannot really reach superconductivity. We don't have a functional that describes our superconductivity, but what we can describe is all the properties in the normal phase. And maybe here, just as my last transparency, in order to understand why suddenly this phase transition happens, let's look here at the hydrostatic pressure. This is a band structure where I have colored the different d orbitals. And here is just below this phase transition, and this is just above. And if you see just below the phase transition, where the system just goes from this orthorhombic to this collapsed trigonal, if you look at the Fermi level, you have here a very flat a very flat bands, which means that you have a very sharp density, high peak density of states at the Fermi level. It means that the system is very unstable. So the system likes to get rid of this feature here. It has not that many options. One, of course, is magnetism, but here we are already at operation where magnetism is gone. So the only option that the system is left with is basically a structural distortion. And this is what it does. It does a structural distortion and gets rid of this instability. So let me just go to my conclusions. By analyzing these electronic properties, we can understand these magnetic and structural phase transitions in these materials, and then make some connection to superconductivity. So as we saw with DFT, we analyzed the normal state. There is, in fact, this system is we have basically magnetism, orbital degrees of freedom, and lattice degrees of freedom play a cooperative role or against each other in order to define the properties of the systems. The systems are multi-orbital systems. From the topology of the Fermi surface, we can understand a few properties of these materials. Magnetic order is properly described, and the iron magnetic moments are very soft. And as I showed you, the pressure-induced phase transition can be very well described with DFT. And if we want to go, and at some point we have to go beyond DFT, and for instance I showed you that DFT plus DMFT can give the correct normalization of the bands, and also we can then understand this reduced magnetic moment. And with that, frustration is for next time. And thank you for your attention.
Great, time for questions?
Are you able to recover the situation at the structural transition before the magnetic transition in the Valenti well?
So at the structural,
We know that the structural is always before the magnetic transition.
right. This is for the and this is what we want to do next, because this is what the result I presented is for the 1 to 2 systems, where we know it's at the same temperature. And the reason why we did these calculations is because for these systems where we have many experiments being done, for the 1111 systems there is not that much done, and that's why. But this is one thing that we want to do. We want to see whether in the 1111 systems we do have exactly what you say, these structural and magnetic phase transition at different temperatures.
They are already on the experiment.
There is one point that I should mention here. If we do DFT only, the point is DFT works at temperature equals 0. So temperature is not a degree of freedom that I have in my calculations, and therefore what I think I will get always with DFT is at the same temperature, so at the same point both phase transitions. And this maybe one can understand because if I have tetragonal symmetry, basically the tetragonal symmetry, any antiferromagnetic ordering is just unfavored, doesn't like it. As soon as I just allow a little bit of orthogonal distortion, then antiferromagnetism just comes in. So that means that I have to go away from t equals 0 if I want to see such effects. If I want to allow maybe possible pneumatic phases, some orientational order, and this, then I should do a finite temperature DFT. But this is, it's an important point that it would be nice to be able to check.
I think this is just out of ignorance. So we know that for DFT there is a theorem that tells me that energy is the unique functional of the density. First question is, what do we know? Does this theorem extend to various correlation functions? Do we know that if one determines this, are they a unique function of density? And the second is there equivalent theorems for DFT plus many-body methods? Because some of the correlations will go one place, some of them
That would be nice. Leap has done a lot of work in getting generalizations of DFT by including not only energy, but also including more functions than energy. So there is a lot of work done by LEAP in this direction, and also finite temperature. At some point you also want to do thermodynamics, finite temperature. So there's a lot done in this direction.
But sorry, the rigorous proofs are all for ground state properties. Is that correct or not?
The original proof is only ground
No,
state.
this I know.
Nice.
Leaves work.
LEAP goes beyond that.
Ah, okay.
And LEAP has done, recently, maybe 10 or 15 years ago, quite a few new works by just extending that to thermodynamics. So there is quite a lot being done in this direction, but DFT plus many body, this is still a problem, and the problem comes because when one does, let's say, DFT plus DMFT, what you do is you do basically the DFT cycle, and then basically what you want to do is to use your wave function, your DFT wave function, and then with these wave functions that just work in the DMFT. And you have the problem that DFT alone already contains some correlation and exchange because of LDA or GGS. So that means that now you try to include extra correlation, and you have what is called this double counting problem. And this is where all the efforts are being put on about this, how do I deal with this double counting? And people maybe sometimes don't say it, but the point is that you can get very different results depending what kind of double counting you are considering. So one has to be very careful with the double counting. And this is one of the reasons why theorems are very difficult to get at this level.
So, and rigorous results are sort of hard to come by because depending on what.
Because of this
Yeah.
double counting term. Yeah.
When you do the calculations of the magnetically ordered moment for the, I forget which system it was, which Nichtide system it was.
Which one?
The one you showed us a function of, I'm thinking of the one you showed us a function of pressure at the beginning.
Oh,
Your
this
early
is the one,
work.
This is the calcium.
That's calcium 1 to 2.
Yes.
No, I meant the magnetic moment as a function of pressure. Your early work.
Oh, yes. This was for the
Yeah. So can you tell us this moment, how it is distributed over the various d orbitals?
Yes, I can.
And
I
is it
cannot tell you now.
is it kind
but
of
I can
just qualitatively? Is it equally distributed? Are there sign
No,
changes?
no.
Are there sign changes?
Yes, we check that. I know that we check that, and you have it. It's not equally distributed between the d orbitals. You have some d orbitals where you have. You can really see basically you have, of course, a pattern, and you can really see that there are some d orbitals that have more magnetic moment and others that have less.
And are there some cancellations?
Within one.
No,
So when you
no, between orbitals.
But between orbitals on the same side or on different sides.
Or let's say on the same side. We're talking about a homogeneous
Yes.
ordered state.
No. Wait. So wait a second. So on the same side, the distribution of the magnet. Let's say if I have 0.7, the distribution changes. So for instance, one orbital may have 0.6, and the other 0.1, and the other 0. But what you're asking is whether on the same side, for different orbitals, you have positive and negative contributions.
If you ever find such a thing. No, you don't. Okay, thanks.
There are some LDA plus U that targeting that.
That are getting this? Uh-huh. Okay, so
I think
this
it's
is...
something that depends on the way you do the double counting, but there are at least 2 or 3 with, I don't know if LDA plus U for sure, I think it's also GGA or GGA plus U, I don't know. There are at least 2 or 3 groups which have reported that kind of results.
I mean, what we did is what you do. I mean, what you can do if you want to get this reduced, and this we did, is GGA plus U with a U negative, which basically with the U negative here and with the certain double counting, what you do is you penalize large magnetic moments, and then you can very nicely get these reduced magnetic moments. But these you have to be very careful and to know what you're doing, because it's not that you are attractive. It means only that you're penalizing, and then you can get very nicely these band structures that I showed to you.
What could be physical meaning?
The physical meaning is, again, it has to do with this double counting. If I show you, I don't have it in this slow, but you know, I can show you afterwards. If you look at your equation, basically what you have is your LDA Hamiltonian plus a term which is u minus j. So if you take the around mean field double counting, u minus j, and multiply by n terms, that basically what you see is that if your magnetization is high, this is just penalizing your energy. If your magnetization is small, then it's favoring your energy. So therefore, you will obtain with that a small magnetic moment. But the physical meaning of that, I mean, you are just sort of mimicking a small magnetic moment. But physically, it's not. It's very dangerous to do that. I mean, there's no physical meaning anymore. It's only that you are adding a term that corrects this large magnetic moment by just penalizing it.
So it's no real physics in it, but
No.
simply just the way to correct for mistakes you
Exactly.
made before, yeah?
Exactly. Yeah.
In the
Silica.
sorry, in the collapsed terminal phase, do you find something, or can you check it if you have some kind of bonds between the arsenics of different layers?
Yeah, I think I can show you maybe these bands that I was showing to you. You see this. I have put this arsenic PZ, right? And you see it here that it comes. So basically, what you're doing here is it comes and you get very strong hybridization. It means that you start really to have this bonding through this arsenic PC. Yeah.
That last week, so Jean-Pierre Tablone mentioned that he's getting some kind of hints on that experiment.
Very nice. Oh, that's nice to know. Thank you. Yeah, I mean, this is basically what you see in the calculation also.
You were mentioning the difficulty of LDA of determining the arsenic height over the plane.
Yes,
And why not if you do the calculation in the magnetic phase, right?
exactly.
Then
Then it's
the
fine.
height comes out.
Yeah, so
Doesn't that mean that actually this is related somehow, the inability of the LDA of describing a magnetic moment in the paramagnetic phase and the structural problem?
yes, this is, I mean, this is, in other words, what I'm showing here with the soft magnetic moments. I mean, this is correct what you're saying, that as soon as I put magnetism, then I get the correct position, but the magnetic moment is just too high. And this is, as you said, the inability of LDA. I have to go to spin-polarized LDA.
Okay, so that's